Those of you that have been away, well, actually, you're just back in the classroom, and it kind of looks like I am, but I'm really kind of not. Creepy, right? Anyway, today we're going to pick up where we left off, and this is going to be on chapter 32 with those big white fluffies, otherwise known as clouds, Tyler's favorite subject. Am I right, or am I right? Yes. So, we're going to pick this up here on clouds. One thing I want to share with you is, just in case you weren't sure kind of what a cloud was, pardon me whilst I recite. A cloud is a visible aggregate of minute particles of water and or ice in the free air. Well, there you go. So, when we think about clouds, a lot of times we look at clouds and we think, oh, aren't they pretty? Oh, look at the big fluffies. They look so soft and gentle. Oh my gosh, I just want to pet one. But sometimes these clouds are not quite as fun-loving as we might expect. So we're going to talk about this. We'll talk about the nomenclature here with regard to clouds. We will also talk about what it says there at the bottom of figure 32.1. about what it is that clouds can actually foretell, and so that's going to be kind of what we sort of work on here on this chapter. So here we go, the naming of the clouds. These are going to be things, guys, that you are gonna need to know. So these are things that you're going to need to put down on your notes, and you're going to have to kind of get these things squirreled away somewhere in your note-taking apparati, and more importantly, somewhere logged in your brain, because these will show up on a quiz near you. So we look at this, and a lot of times the clouds, the way that we name them, has to do with the level that you might find some of these clouds. For instance, high-level clouds, these are going to be bases at approximately 20,000 feet. Remember, guys, that anytime that we're talking about our altitude, any altitude at 24,000 feet or above is always going to be frozen. So it's always going to be below zero at 24,000 feet and above. Sometimes just below that at 22,000 feet, the air may not actually be below freezing, just kind of depends on the time of year. In the mid part of the summer here in sort of our latitudes, it may be a little bit warmer than that. So, but just kind of know that. And so when we look at this, we look at those high-level clouds, again, with bases of approximately 20,000 feet and up, by the way. Those are always going to be composed primarily of ice crystals. And so when we look at those, we talk about these as being cirrus clouds, cirrocumulus, cirrostratus. You kind of see the prefix there of those high-level clouds. You will note the cirro prefix, C-I-R-R-O, that's going to be the prefix. So those are going to be clouds 20,000 feet, bases 20,000 feet and above. So then we look at mid-level clouds. Mid-level clouds, you may have a base of approximately 6,500 feet, and these have the prefix alto. I don't know how many of you have been in a choir, but you know, those are kind of the things there that, you know, when you have an alto, that's kind of the thing. By the way, I am actually going to walk out here to the door and find out who's beating on the wall, because it's just kind of annoying, but that's sort of the thing. Hey guys, I'm recording a class in here, so would you not beat on the wall, please? That's very nice, thank you. So anyway, alto is going to be those clouds at like 6,500 feet and above. So in those cloud layers that you have, where you have the clouds in that 65 to sort of 1,000 range through there, that's going to have some form of a prefix of alto. Okay. Now then, we look at low-level clouds. Well, the low-level clouds is you have a prefix of strato or stratus, and those are going to be clouds 6,500 feet or below. So it's kind of interesting, because I had always sort of had this feeling of like strato as being stratosphere and being just way up high, but I was wrong. They're kind of down low. So when we look at these again, you'll see that these lower level clouds, 6,500 feet and lower, are going to be these stratoclouds, stratus. In some cases, you'll find what they call a fair weather cumulus. It may just be this lone little puffy out there all by itself, and that could be in that strato layer there. Even some rain clouds that are not necessarily thunderstorms, that might have enough precipitation in them to be sort of this low-hanging kind of a rain, kind of an angry-looking cloud out there, and that could also be a nimbostratus cloud. So just keep that in mind. If you look in the margins here, and we look at these here as 4 categories. Well, before I get there, let me talk about the 4th. Duh. Clouds with extensive vertical development. So what does that mean? Well, that's going to be a cloud that has been subject to some form of enough atmospheric instability and enough lifting action for this cloud to be really, really tall. So this cloud could have a base somewhere at like, 8,000 to 10,000 feet, and it could extend upwards above 50,000 feet. There are some thunderstorms on record that have had cloud tops in excess of 60,000 feet. Now, boys and girls, that's a big old cloud. So just know that the stuff going on inside those clouds, you don't want any part of that with an airplane. It doesn't matter what size of an airplane, because that's just bad juju. Okay. Now, these are 4 families here according to the altitudes: high level, mid level, low level, and those with extensive vertical development. So know that. No cirrus, no altos or stratus, okay? And then the low vertical ones. So now we look at the clouds named according to the following types. So if you look at these bullet points here, and I think there are 7 of them, you'll see like these cirriform, C-I-R-R-I form, kind of a fibrous looking cloud made of ice crystals, cumuloform, or kind of that heaping cloud that looks like the big cotton balls, looks like cauliflower out there, stratiform, layered clouds, primarily a sign of kind of more stable air, nimbus, that is going to be clouds that are going to get you wet. Fractus, they're going to be some form of a fragmented cloud out there, something that looks kind of like a broken picture that you might see. Castellanus, these are going to be kind of clouds that you see. They can be somewhat, have kind of some vertical movement, but you kind of see them in lines with those. And then lenticularis. Lenticulars or lenticularis, those are the clouds that you see a lot of times over mountains, or that you see on the lee side of the mountains. Remember, you have the windward, here's the mountain, and then over here is the lee side. You will see those lenticular clouds that are standing over those mountains or just east of those mountains, indicating what? High winds. So those are going to be the forebearers of high winds and perhaps a lumpy ride. So those are going to be clouds that we're going to be talking about here in this chapter. So you can read these. You'll read here about the clouds. There are going to be some clouds, as they mention here in the margin, that are going to be just fine to fly through, while others may not be. And it's very, very important to know the difference in kind of what clouds you want to fly through. Because again, remember what these clouds are. These clouds, it's a form of a visible moisture. Now it could be high enough and the air could be cold enough that icing is not going to be an issue. Everything is frozen and nothing is going to stick to your aeroplane. But you can be down within a certain width of temperature, so sort of we're talking Celsius here, 5 degrees above Celsius and then 15 below Celsius in that band, where those temperature ranges and that temperature band with visible moisture are the ranges there where we primarily associate that with aircraft icing. And we want to try to avoid those areas whenever possible. So that's kind of it. Unless you have an aircraft that is completely geared to keep that ice off your airplane, or get the ice off the airplane and keep it off the airplane, you want no part of that, because that's just, again, that's just more bad juju. So, moisture in the atmosphere. You can talk about this. You guys can look. I'm sure you have read this. And you look. Everybody understands, at least you have had some form of earth science there that has talked about the 3 states of water. And you have vapor, you have a liquid, and you have a solid. And you can get these things to go back and forth between one and the other. The biggest things that we look at is just understanding what type of precipitation that we're talking about here. The size of the droplets oftentimes dictate the nomenclature. And, also sort of what is the current state. Is it a vapor? Is it a liquid? Is it a solid? And sometimes you can have ranges there where it's sort of kind of in between, and you're thinking, what the heck is that? Well, there are times that water droplets can be somewhere between a liquid and a solid. And this is what we'll talk about later when we talk about supercooled water droplets, because those supercooled water droplets are actually liquid water that is actually still below freezing but not yet frozen. How does that happen, you ask? We'll get there. And then as your airplane passes through there, it sticks to that airplane, and that can be just a complete nightmare when it comes to aircraft icing. So keep that in mind. You guys can look at those three states. You can look at that. We talked about virga before, relative humidity. This is a thing about where we might talk about the amount of water vapor that we have in the air. We know that warmer air can hold more water vapor because there's more room between the actual air molecules, and so the water vapor, the little actual water molecules, can fit between there. Well, when those air molecules are squeezed together because of the temperature changes, then it squeezes out that water, and that water is squeezed out in the form of some form of visible moisture. So there you go, you've got that there as well. We don't get a lot of humidity here. A humid day, excluding times right after a rainstorm out here perhaps. I mean, it might be 65% humidity, might be a humid day for us. It's not uncommon for humidity here to be in the 20%, or even in the desert, it can be 20%. It can be really, really low. So that's kind of, the things that we have to think about. Down in the lower states, coastal areas like that, places that are oftentimes more near water than others, they're going to be more humid. So you have to kind of think about that. Glaciation. Glaciation, I don't say that there very well. One of the things that happens is that when you have water vapor in a free air, when you have temperatures that are above a temperature of -40, it says here that the water vapor in the free air essentially never sublimates directly into ice crystals. It nearly always goes through a liquid phase first here. So whether or not that's part of a process of conversion into ice crystals when those ice crystals start, and that really depends on, what kind of air we're talking about. The more humid, clearly, the quicker that process can occur. The big thing is that, if you think in terms of that glaciation that we talked about, in some cases, you need some kind of a mechanism for that conversion to a solid to occur. Well, slamming your plane through that air mass and in through those supercooled water droplets that I just talked about leads to that form of that glaciation. You've heard of glaciers, that frozen water kind of stuff. And it actually causes that water to go ahead and freeze because it's on something now. And that's just bad juju. You guys can start reading that. Cloud formation. Again, we understand what forms a cloud. We've talked about that a ton. We talked about warm air. We've talked about dew point. You guys can read that. We have talked about that a ton. Okay. So adiabatic processes. When we talk about the adiabatic, it says here in the book as well that in adiabatic process, temperature can change as a result of pressure changes, even though heat energy is neither added nor taken from the system. Expanding a gas or decreasing its pressure causes a lowering of temperature because fewer molecules will collide with that measuring surface. How many of you guys have ever used an aerosol bottle and you have you've kind of looked at sort of that exothermic process Is it exothermic or endothermic? I don't know, Tyler, you tell me which one this is. And you spray kind of this aerosol, and depending upon what the propellant happens to be, as that can kind of loses then that gas and therefore that pressure, then that can gets really cold, right? So again, why did that temperature change? Why did it change? Well, because again, it has to do with the differential now in pressure. The inside portion of that can is not under as much pressure anymore, and so therefore you're going to get a change in a temperature. It's similar to like this with the adiabatic process. So if you guys look at this here, you can read this. The adiabatic process kind of involves that expansion of a gas and its cooling when it's in when that parcel of air rises in the atmosphere. And you know, a lot of things can happen as to cause that. But some of it can happen as that air rises from instability. That air can also, that rising air can also be caused, as we talked about in class yesterday, about the orographic elements of the lifting action due to the geography there as well. But the things that I want you to be aware of here is this. Normally, air will cool at approximately 2 degrees per 1,000 feet. That is where the temperature drops approximately 2 degrees per 1,000 feet. Now, it says here that unsaturated air will cool adiabatically at about 3 degrees Celsius per 1,000 feet as it rises and expands. This is known as the dry adiabatic lapse rate, or DALR, 3 degrees Celsius per 1,000 feet. Okay, that is the dry adiabatic lapse rate. So now, if you look at this, on the saturated adiabatic lapse rate, saturated, or SALR, that changes its value about half of the dry, and so the saturated is going to change 1.5 degrees Celsius per 1,000 feet. Okay? Standard is 2 degrees Celsius per 1,000 feet. So again, remember, dry, DALR, 3 degrees per 1,000 feet. Saturated, 1.5 degrees Celsius per 1,000 feet. Okay, so just keep that in mind. When we look at this, of the types of clouds that may form, it has to do with the stability of the air. That stability of the air, in most cases, will actually be the genesis of what kind of a cloud it's ultimately going to be. So if you look at moist, unstable air that continues to rise, this is where you get these cumulus type clouds. And the more instability that you have, the lifting action, and if there's enough moisture in the air, clouds like that can indeed turn into some form of thunderstorm. Now again, you look at these clouds, and from the ground you look up and they just look so light and fluffy, and it's just awesome. And even from the air, as you fly by these clouds, you look and you have some of these big, tall cumulus clouds that you can see. They don't look like thunderstorm clouds. They don't look too bad. Wouldn't it be fun to fly through those? Well, some of those clouds you actually can fly through. But sometimes they're a lot more than fun. They can be awfully entertaining, as like with stuff flying around the cockpit. Because why do these clouds exist? Why does a cumulus cloud exist? Instability and some form of lifting action. That's why that cloud is there. So if you fly through or under that cloud, you can expect a lumpy ride. Okay, because again, the reason that those clouds are there is because of that lifting action underneath it, creating the cloud. These are the times where if you can be over those clouds, your ride could be a lot smoother. So, keep that in mind. Unstable air. 4 bullet points here. These are things you're going to need to know. Turbulence from rising air, cumuliform clouds, showery rain from these clouds, which again kind of mixes up with the air, and the air direction is the rain, and the precipitation falls. And the other thing with that unstable air is just that, remember, at times, even though that you do have that instability, you may have some pretty good vision. You should be able to see quite a bit. You know, it's that thing, it's like where that air is so clear, and like sometimes the rain, especially in the desert Southwest, kind of flying after a big rainstorm, and that rain has kind of gone through the lower levels of the air and kind of scrubbed a lot of the dirt and the sand and all that stuff out of the air, and it just looks so clear. It's just, it really is gorgeous. But sometimes that can also be, you know, because of the instability there, it can be a little bit of a rough ride. Stable air. Stable air is going to be the thing where the air masses are not moving quite the same, ergo the stability. But chances are you might have a better ride, but your visibility may be poor. And that's what they're talking about here in the margins here with regard to stable air. These stratiform clouds, or those layer type clouds like they're talking about, the reason that they are layered like that is because there's not a lot of lifting action, okay, to kind of make them anything else. You'll kind of get, because of the fact that things aren't moving too much underneath, it could kind of get a lot of particulate matter in the air itself, and so the visibility might not be too good. However, because of the fact that that mass is somewhat stable, the flying conditions will probably be better. So just kind of keep that in mind. We talked about these. We talked about the lapse rate. So in a standard atmosphere, as I mentioned before, the standard atmosphere, you're looking at a lapse rate of 2 degrees Celsius per 1,000 feet. So, you know, that's kind of it. And by the way, 2 degrees Celsius, I want to say that's 4.4 degrees Fahrenheit. I want to say that. I don't know why, but I'll try to look at that. Cloud types, cloud formations, again, we look at that sign of that unstable air is going to be that big puffy, the big fluffy cloud out there. And then the more layered type of cloud, that stratus type cloud, is going to indicate you know, more stable air. Now, with the lenticular cloud, especially the standing lenticular clouds, I will take exception to those indicating stable air, because it's a little bit different. You still have air masses that are moving kind of in the same direction, but they are moving pretty doggone quickly. So the things that you have to be aware of is that what is out there forming these clouds. With standing lenticulars, it's high wind. We'll talk about how those form here in a little bit. Yeah, 4.4 is about 2.5 degrees Celsius. So this is a way that you can kind of run some calculations to determine what the cloud bases are if you know the temperature and the dew point. So if we look at this, so if you look and you're trying to figure out the cloud base, normally with air temperature like this, they use 2.5 degrees Celsius or 4.4 degrees as being kind of that lapse rate for every 1,000 feet. So if you know the temperature and you know the dew point, you can calculate the cloud bases of the clouds above you in AGL, okay? And these are going to be an AGL type of measurement. I think they talk about these here in a second. Yep, here's some examples. So you guys can look at this and you can see that in this example here, example 32.1, you can see that you have a temperature of 17 degrees C, the dew point is 12 degrees C. What's the spread? The spread is 5. So if you look at this and you think about 2.5 degrees Celsius per 1,000 feet before you reach the dew point, then what's going to happen is that you know that every 1,000 feet the temperature is going to drop 2.5 degrees Celsius. So if you go up 1,000 feet, there's 2.5. Another 1,000 feet, or a total of 2,000 feet, that's 5 degrees. What's the spread? 5 degrees. So there it is. Bob's your uncle. 2,000 feet. AGL is where you can expect the bottom layer of those clouds. These are some others here. I'm going to let you play with these. You will also find examples of this also in big blue. So you look at these, they will throw these out at you with a Celsius example as well as a Fahrenheit example. Just remember that the Fahrenheit example is going to be the 4.4 degrees, whereas the Celsius typically is going to be either 2 degrees or 2.5 degrees Celsius. So you can run some of the math there on your own. Clouds with orographic lift. Lenticular cloud, here we go. Why are these for us in the mountains particularly of particular interest? Well, because they can be that forebearer or that indicator of high winds over these mountain ridges. So sometimes we may not feel the effects of those winds down in the valleys down below us. But as you start getting aloft and you start getting up here somewhere near or above the ridges of these mountains, you're absolutely going to feel it. So it's a thing where you really have to pay attention. So if you look here, as these winds fly over these mountains here, you can see that you have these areas where the wind's moving the air up, cooling the air, reaching the dew point. Here you now have a cloud. You can see the bases of the cloud, and you see the tops of those clouds kind of shaved. So they kind of have this convex look to the top of them, and sort of they'll describe that as somewhat of an almond shape cloud, or kind of a convex lens shaped thing of the cloud over the top of it. And what happens is that you have that air that's moving rapidly over the top of those, and that cooling air from underneath forms the base of those clouds. So you have to know there is fast-moving air that's making those clouds appear. Sometimes you can use that to your advantage. Other times it can be a real nightmare, depending upon the direction that you're flying. We know that most air masses move from west to east. So I have flown in situations, in fact, when I brought 141 Hotel Lima back from Canada, I got in what we call kind of a mountain wave, which it actually exists when lenticular clouds, they may or they may not be present during mountain wave activity. But this is where you have this up and down motion of this fast moving air. I had 50 knots on the tail, but I was also getting pushed down and up, so I wasn't able to maintain altitude. The first thing I did was disconnect the autopilot, because what it tried to do was hold my altitude. Well, if it tried to hold the altitude while it was forcing me down, what's it wanting to do? It pitches up, pitches up, pitches up, ultimately until it'll stall. And that, of course, would be kind of a bad thing. Then, as that rapidly moving air is pushing you up, it wants to nose over to hold that altitude, nose over, nose over, nose over, and it can be, well, it can get your attention. So what you have to do is you disconnect the autopilot, keep your wings level, and you take, as long as you can, terrain permitting, that kind of up and down motion of that air as it moves you along. In some cases, it may not be that bumpy, because all of that air is kind of all moving together. And so you kind of have to know where you can and where you can't get into kind of that mountain wave piece. Now imagine trying to fly back this direction in that mountain wave and flying into that 50 or 60 knot headwind. This exact same thing happened when Mr. Kraft and I were taking my airplane over to the Fort Collins Loveland airfield to have some avionics work on it. We had some winds aloft at 15,000 feet of greater than 50 knots, and there were tons of lenticular clouds out there that day. So flying out there wasn't that bad. It wasn't until we got on the lee side of the mountains over there near Fort Collins that we really started getting our butts handed to us. So we got the airplane delivered, and then we were flying the Diamond back. So here is Mr. Kraft and I. Stand by. This is why producing these videos in this classroom can be problematic. Anyway, So coming back, it's Mr. Kraft and I in this airplane. We were not at full fuel. Our weight and balance was good. Now just kind of remember that when I get in one of these diamonds, I'm adding quite a bit of weight to it, you know, about a smooth 250. So there's Mr. Kraft and I. We're flying, we're actually kind of flying sort of a tacking course, kind of flying to try to get as much altitude as we could before we got up and tried to get over the mountains. We were trying to get up over the particular passes at least 14,000 feet. We were trying to get to somewhere near 14,500, but it was hard for us to do that because of the fact that we would get this lee side pushing of this air and would attempt to keep pushing us down. So we had to extend our flight quite a ways north and kind of tack kind of back and forth to gain altitude before we had enough to get enough sufficient altitude over these ridges. And I think that pass was like at 12,000 feet that we were crossing over there, just kind of northwest of Loveland. And it was at about 12,000 feet, but we wanted to be at least 2,000 feet above it so that we would not get caught in this wave as it gets pushed over that mountain. At one point, we had about a 30-knot forward ground speed. 30-knot forward ground speed. We were crawling. That was that wind. And so you have to really kind of pick and choose. This is one of the coolest things about you kids learning how to fly here in Aspen, is the fact that you learn that mountain flying weather. Now, that type of weather is nothing that we would ever send an inexperienced pilot out in that kind of conditions. When we have winds coming over the ridges greater than 30 knots, we are a no-go. So just keep that in mind. The more experience you have, knowing that you have outs, all of these things, a lot of this stuff, and I don't even know that I would have done that were I not with Mr. Kraft, who has forgotten more about mountain flight instruction than I'll ever know. So that was just one of those things that I just wanted to share with you. So, standing lenticulars, signs of high winds over these mountains. Okay, here's the wave. So you get this wave that kind of pushes out. The mountain wave coming from the Rocky Mountains, there have been days that the wave effect has existed as far as eastern Nebraska. That mountain wave can be huge, and it's not just for low-flying aircraft. High-flying aircraft flying in the low 30s, they can also be part of that mountain wave as well. If you're flying from the west to east, you know, that's not a bad thing, you know, because you get a nice tailwind. But coming back from the east to the west, you know, it can really get lumpy and slow you down. So underneath the ridges of those, as I was telling you here before, you can see some other things here. You want to be above those ridge lines well ahead of when you need to cross them. You can't just determine, okay, if I continue my rate of climb just like this, I'll cross that ridge at 500 feet. That's not the way to do it. When it's windy like that, you have to be above that ridge line, and you cross that ridge line at a 45-degree angle. You do not cross it perpendicular. You cross the ridge at a 45-degree angle, because if for whatever reason you get a downdraft, you only have to turn here 90 degrees from this to actually begin flying away into lower terrain so that it doesn't push you down into this mountain ridge. So that's why you cross those ridges at a 45-degree angle. You never cross them perpendicular, always at an angle, because you always want to leave yourself an out, okay? So with these, as we look here before, if you look, sometimes on the lee side of mountains, and in some cases it can be kind of at about the same level as the peaks of the mountains, but a lot of times it will be actually below the mountains, and you'll get this rotor cloud. A rotor cloud is going to be this big, long, horizontal cloud. It kind of looks like a rolling pin. Well, it is actually rolling. And that whole thing, it's like a sideways tornado. You never want to fly into a rotor cloud. That would be bad. And then underneath that, you have all of this turbulence caused from the downwash of this air that all it wants to do is to shove everything down into the rocks. So you definitely do not want to be down where that airplane is shown there on figure 32.7. You want to be up and above that and crossing that at least 2,000 feet above that ridge, at least. Okay, the Chinook or the föhn effect. Föhn. This is that thing where you have kind of this, you guys may have heard of these Chinook winds, and you guys have heard of some of these other weather phenomena. You know, you've heard of the, you know, the El Nino, El Niña, some of this Chinook winds here. So you guys can read here and look at what the Chinook winds can actually do. One of the things here is that as you look at this, is that when you have these winds, and like for instance, if you have got a lot of moisture-laden type of clouds that you have, if they're shoved orographically up over a mountain range, well, what's going to happen? Well, you know, that air is going to cool. The moisture is going to precipitate out, and here you have clouds and you have water, and you can have storms over there on the windward side. While on the lee side of it, now you may have a little cloud cover over there, but now this air is dry because it's given up all of its humidity, it's given up all of its water vapor and water on the windward side, and on the lee side it just gets dry. Well, it's one of the things that kind of happens, I was told, sort of in the Hawaiian Islands, like in Kauai. In Kauai, it's the most amazing mix of earth science, I think, that there may be. Because on one hand, you have areas of that island that are just complete rainforest. And the amount of rain that they get, they measure that in hundreds of inches a year. While on the west side of it, it's desert. It hardly gets any rain at all. And it's just one of those things that it just has to do with the winds, and it has to do with where all of that energy, where the moisture and those clouds lose their energy, and that happens over these certain peaks. And then by the time that it gets over here on the other side, it's got nothing except maybe shade. So, you know, that's kind of part of that. California gets a lot of that, I think, too. Clouds formed by turbulence and mixing. Oh, well, we see a few of those out here, don't we? So you can look at those. Turbulence clouds. I don't know that I've ever actually seen something that's been referred to as a turbulence cloud, but clouds that can be formed by, you know, that unstable air. These are some kind of things that you see here. So for instance, if you see like a warm front, remember how I told you that a warm front kind of goes along where it kind of comes in and just kind of squishes that cooler air out from in front of it like that. This is where you can see clouds with more horizontal types of clouds actually being pushed further and further vertically. It's not necessarily caused by that lifting action like you might see a big cumulus cloud, but it's caused by the fact that it just sort of gets pushed up as it kind of takes the place into that cold front, and this is where you get that continuous rain or snow, but it's normally not associated to hazardous weather necessarily, that reduced visibility to be sure. It's kind of where you start to see some of the virga, and you see that rain coming in with that warmer air above, the cooler air below, the mixing dew point. Rain begins to fall, but it never reaches the ground because it's absorbed by the dry air underneath it, and it never reaches the ground. We would see that in New Mexico all the time. Oh, and always be aware of the dreaded latitudinal pinching of air masses. Latitudinal pinching. Pinching. Precipitation from clouds. Those can come in a lot of different flavors. Rain, drizzle, snow, hail, freezing rain, dew, frost, or ice. Okay, so you're going to need to know all of those different types. Okay. Showers falling from cumuliform clouds. Okay. Showery precipitation here. This steady precipitation from stratiform clouds. They call it non-showery. Okay. Virga, we talked about that. A lot of times you might be riding with somebody and they'll see some virga off in the distance and they'll say, hey, let's go wash the airplane. Probably not a good idea. I've heard of that happening. So, again, the lifted index, going to look at that there, lifted index, lifting, and there we go, there's the review of the clouds, okay? So there's that. That is chapter 32. You guys can take a look at that, the nomenclature of the clouds, the layers, the families, how they're formed, and then we also get into that here on the next chapter with icing. So what we're going to do is we're going to stop this one because this is chapter 32. Now I'll record a segment here on chapter 33. Okay? So there you go. See you soon.